Imagine standing on a world where the sun appears 3 times larger than it does from Earth, hanging motionless in a pitch-black sky. A world where temperatures swing from scorching 800 degrees Fahrenheit to freezing -290 in the span of a single day. This isn't science fiction. This is Mercury, the solar system's smallest and most mysterious planet, a place of extremes and enigmas that defy explanation. Despite being our closest planetary neighbor to the Sun, Mercury remains one of the least understood worlds in our cosmic backyard. Its surface is scarred with craters, its core is strangely massive, and its thin, wispy atmosphere offers no protection from the relentless fury of space. But the strangest part, the more we learn about Mercury, the more questions it throws our way. Today, we're embarking on a journey to uncover 25 of Mercury's most baffling mysteries, phenomena that challenge everything we thought we knew about planet's gravity and even the origins of our solar system. Why does this tiny world have a magnetic field when larger planets like Mars don't? What caused the massive cliffs that zigzag across its surface like cracks in a broken mirror? And how is it possible that water ice exists in its polar craters, just a stone's throw from the sun's blistering heat? These aren't just curiosities, they're cosmic puzzles that could rewrite the textbooks. From unexplained gravitational anomalies to the bizarre hollows that glow like celestial fireflies, Mercury is a world that refuses to play by the rules. Every mission we send there, from Mariner 10 to Messenger, brings back more head-scratching data than the last. So buckle up, because we're diving deep into the secrets of this tiny titan, where every discovery leads to another question, and the truth might just be stranger than anything we've dared to imagine. This isn't just a tour of a planet, it's a detective story written in the stars, and you're about to become part of it. One of Mercury's most bizarre features stares back at us like glowing pits of light scattered across its cratered face, landforms scientists call hollows. These strange, shallow depressions resemble something from a surreal painting, their bright, almost pearly interiors contrasting sharply with the planet's dark, rugged terrain. Unlike typical impact craters or volcanic basins, these hollows seem almost freshly formed, as if the ground simply collapsed inward overnight. Some span just a few dozen feet, while others stretch for miles, clustering in chaotic groups like celestial honeycombs. What makes them even stranger is their composition. Studies reveal they're rich in volatile materials like sulfur, chlorine, and even sodium, elements that shouldn't survive long under Mercury's blistering sun. The prevailing theory suggests these hollows form when underground deposits of volatile compounds, perhaps ancient layers of primordial material, are suddenly exposed to space and vaporize in the vacuum, leaving behind these ghostly cavities. Imagine a block of dry ice left on a table, slowly vanishing into thin air without a trace. But here's the puzzle. These hollows appear geologically young, with sharply defined edges showing little erosion, meaning this process might still be happening today. That raises a tantalizing question: what could possibly be replenishing these volatile substances on a planet so close to the sun, where surface temperatures could melt lead? Some scientists speculate hidden reservoirs of volatile rich material might lurk beneath Mercury's crust, periodically venting to the surface. Others wonder if micrometeorite impacts continually churn up ancient layers we've yet to fully understand. Even more perplexing is how these hollows defy traditional planetary geology. On most rocky worlds, surface features erode over time, worn down by wind, water, or tectonic shifts. But Mercury has none of those, just endless bombardment from solar radiation and the occasional meteor strike. Yet its hollows seem almost alive, changing in ways we can't yet predict. Could they be evidence of some unknown geologic process unique to Mercury? A clue to the planet's chaotic past? Every image sent back by spacecraft like Messenger deepens the mystery, showing hollows glowing like beacons in a landscape frozen between destruction and rebirth. One thing's certain, These unearthly formations are more than just oddities. They're a window into the untold stories buried beneath Mercury's sun-scorched skin. Beneath Mercury's battered surface lies one of the solar system's greatest cosmic riddles, a core so massive it defies all expectations. This tiny planet, barely larger than Earth's moon, somehow packs an iron heart that makes up nearly 85% of its entire radius. For comparison, Earth's core accounts for just half its diameter. This isn't just unusual, it's an outright contradiction to how rocky planets are supposed to form. How could Mercury, the smallest world in our solar neighborhood, end up with such an absurdly dense interior? The answer might rewrite everything we know about planetary birth. One leading theory suggests Mercury was once a far larger planet, perhaps double its current size, until a cataclysmic collision with another protoplanet blasted away its outer layers. Imagine a cosmic wrecking ball shattering a planet's crust and mantle into space, leaving behind nothing but a stripped-down core cloaked in a thin shell of debris. This would explain the bizarre density measurements. Mercury isn't just dense. It's practically a naked iron sphere wearing a geological trench coat. But there's a catch. If such an impact occurred, where's the evidence? We'd expect to find traces of ejected material elsewhere in the inner solar system, yet no debris field matches the scale required. Another hypothesis paints an even stranger picture, that Mercury formed uniquely from the start, coalescing from metal-rich dust grains near the young sun's furnace-like heat. In this scenario, intense solar radiation may have vaporized lighter elements like silicates before they could clump onto the growing planet, leaving behind a metal-heavy world by design. Recent MESSENGER mission data adds fuel to this theory, revealing Mercury's surface is surprisingly rich in sulfur and potassium elements that should have boiled away under extreme heat. This leaves scientists scratching their heads. Did Mercury form under conditions we've never seen replicated elsewhere? The mystery deepens when we consider Mercury's active magnetic field, a feature typically powered by a liquid metallic core. Mars, twice Mercury's size, lost its magnetic shield billions of years ago as its core cooled. Yet somehow, this diminutive world's core remains partially molten, another puzzle layered atop the first. Some researchers speculate tidal forces from the sun's gravity might help keep Mercury's core churning, while others propose radioactive elements could be providing unexpected internal heat. Every explanation raises new questions, turning what should be a simple case of planetary proportions into a cosmic detective story with missing clues. What makes this enigma so thrilling is its ripple effect across astronomy. If we solve Mercury's oversized core, we might uncover entirely new planetary formation pathways, processes that could explain metal-rich exoplanets orbiting distant stars. This isn't just about one oddball world, it's about rewriting the rules of how planets are built. Until future missions like Europe's BP Colombo probe peel back more layers of this mystery, Mercury's iron heart remains one of the solar system's most tantalizing secrets, a reminder that sometimes the smallest packages hold the biggest surprises. On the opposite side of Mercury from the colossal Caloris Basin, the planet holds one of its most bizarre geological secrets, a nightmarish landscape scientists call the chaotic terrain. This region looks as though some cosmic force took a hammer to Mercury's crust, shattering it into a fragmented maze of jagged blocks, deep fractures, and tilted plateaus. It's not just rough or heavily cratered, it's fundamentally disorganized, as if the ground itself convulsed and never settled back down, the strangest part. This chaos isn't random. It forms a near-perfect antipodal mirror to Caloris, precisely on the other side of the planet, suggesting a connection between the two that defies simple explanation. The leading theory paints a dramatic picture. When an asteroid or protoplanet smashed into Mercury billions of years ago, creating the 800-mile-wide Caloris Basin, the impact was so violent it sent seismic shockwaves racing through the entire planet. These waves would have converged at the exact opposite side, colliding with such force that they literally scrambled the landscape like an eggshell cracking inward. Picture dropping a pebble into a pond. Ripples spread outward until they hit the edges and rebound, creating interference patterns where they meet. Now imagine that pebble is the size of a mountain, the pond is a planet, and the rebounding ripples carry enough energy to fracture bedrock on a global scale. That might explain why the chaotic terrain appears so violently disturbed, with some blocks of crust thrust upward while others slumped into gaps like a planetary scale game of tectonic dominoes. But there's a twist. Some researchers argue seismic waves alone couldn't account for the sheer scale of destruction. Instead, they propose the impact might have triggered something far more profound, a mantle upheaval. Mercury's partially molten core could have sloshed like liquid in a shaken bowl, sending plumes of hot material surging toward the antipode. This would explain why the chaotic terrain shows signs of both fracturing and subsidence, as if the ground collapsed while being torn apart from below. Recent topographic maps from the Messenger mission reveal another clue: unusual pit-like depressions mixed with the jumbled blocks, hinting at possible volcanic activity or outgassing events adding fuel to the chaos. What makes this mystery even more compelling is the absence of similar features elsewhere in the solar system. Mars has its own odd terrains, and Earth's crust bears scars from ancient impacts, but nothing matches the sheer concentrated madness of Mercury's antipodal chaos. Was this a one-of-a-kind planetary trauma, or does it hint at a forgotten chapter of extreme planetary violence early in our solar system's history? Until we land probes amidst those fractured plains, the chaotic terrain remains a silent witness to one of the most catastrophic events in Mercury's past, a planetary quake frozen in time, waiting for us to decode its story. Mercury's magnetic field is a cosmic paradox, a phenomenon that shouldn't exist yet stubbornly persists, defying our understanding of how planets work. Here's what makes it so baffling. Magnetic fields are typically generated by molten metal churning in a planet's core, creating a dynamo effect. Larger worlds like Earth can maintain this process because their massive cores retain heat for billions of years. But Mercury, it's barely bigger than our moon, with a core that should have cooled and solidified eons ago. Yet spacecraft measurements confirm its weak but undeniable magnetic field, about 1% as strong as Earth. This isn't just a mild anomaly, it's a fundamental challenge to planetary science. The mystery deepens when we examine the dynamo theory, the idea that a planet's rotating, conductive core generates its magnetic shield. For Mercury, the math simply doesn't add up. Its core, though disproportionately large, should have lost enough heat over 4.5 billion years to stop flowing. Without that liquid motion, the dynamo effect should sputter out. And yet, Messenger mission data revealed something extraordinary. Mercury's magnetic field isn't just a relic of the past, it's asymmetrical, lopsided in ways that suggest active, ongoing dynamo activity. Imagine a flashlight flickering weakly but steadily in a storm, powered by a battery that should have died centuries ago. Scientists have scrambled to explain this enigma. One radical proposal suggests Mercury's core might be snowing iron, a process where heavier elements crystallize and sink toward the center, stirring the remaining liquid metal like snowflakes falling through water. This slow-motion churn could theoretically sustain a weak dynamo. Others point to tidal forces from the sun's gravity flexing Mercury's interior, generating just enough friction to keep pockets of the core molten. Then there's the wild card, radioactive elements like potassium or thorium decaying in the core, providing an unexpected heat source. Each theory has gaps, leaving researchers chasing shadows in a planetary puzzle with no clear solution. What makes this magnetic quirk even more crucial is its implications beyond Mercury. If a small, ancient world can sustain an active field against all odds, what does that mean for exoplanets orbiting close to their stars? Could there be countless Mercury-like worlds out there, clinging to magnetic shields we assumed were impossible? For now, Mercury's defiant field remains one of the solar system's great unsolved riddles. A humbling reminder that even our nearest planetary neighbors still guard secrets capable of rewriting the rules. In the blistering inferno of Mercury, where surface temperatures can melt lead, one of the most improbable discoveries in solar system history lurks in permanent darkness: water ice. Not just traces, but thick sheets of it, hidden in deep polar craters where the sun's rays never reach. These shadowy sanctuaries, some chilled to -300 degrees Fahrenheit, act as cosmic freezers, preserving water in a world otherwise defined by scorching extremes. But how did ice end up on a planet where daytime temperatures could vaporize it in seconds? And why does some of it appear suspiciously pure, defying all expectations? The leading explanation points to Mercury's chaotic history of bombardment. Comets and water-rich asteroids, remnants from the solar system's violent infancy, likely slammed into the planet over billions of years, depositing water molecules on its surface. Most would have quickly sublimated into space under the sun's withering glare, except in these rare craters near the poles where towering rims cast eternal shadows. Picture a gambler tossing coins into a bottomless pit where only those landing in a narrow slot survive. Over eons, these accumulated water molecules built up as ice, sheltered from destruction. Radar scans from Earth first hinted at this possibility in the 1990s, showing strangely bright reflections consistent with ice deposits. Decades later, NASA messenger spacecraft confirmed it, mapping frozen reservoirs in craters like Prokofiev and Kandinsky, some spanning miles across. Yet not all the ice fits this tidy narrative. Some patches appear far too clean and reflective, almost as if freshly deposited. Water ice exposed for millions of years should accumulate a dark layer of dust and organic material from micrometeorite impacts, yet portions of Mercury's ice gleam like newly fallen snow. One radical theory suggests underground water might still be seeping to the surface through cracks, replenishing the deposits in a slow but steady trickle. Others propose that hydrogen atoms from the solar wind could chemically bond with oxygen in Mercury's minerals, creating new water molecules directly on the surface, a process observed in labs but never proven on a planetary scale. The plot thickens when we consider the ice's bizarre distribution. Some craters house thick, concentrated ice sheets, while neighboring depressions sit eerily empty. If cometary impacts delivered the water, why isn't it spread more evenly? Could Mercury's tenuous exosphere, its wispy outer atmosphere, somehow guide water molecules toward specific cold traps like an invisible cosmic plow? Or do hidden geologic factors like subsurface heat or chemical reactions actively sculpt where the ice can cling? What makes this icy enigma so revolutionary is its implications for life's ingredients in the universe. If water can survive in the solar system's most hostile environment, where else might it lurk unseen? Future missions like the joint European and Japanese BP Colombo probe may finally crack this frozen cipher. Until then, Mercury's polar ice remains a dazzling contradiction. A desert world hoarding glaciers in the dark, proving once again that nature's rulebook has pages we've yet to read. Among Mercury's many geological oddities, few are as puzzling as its ghost volcanoes, strange, dome-like structures that hint at fiery eruptions from the planet's past, yet leave behind none of the telltale evidence we'd expect. On Earth, volcanoes announce their presence with dramatic lava flows, sprawling ash fields, and conical peaks. But Mercury's volcanic remnants are spectral by comparison, their origins whispered rather than shouted. Some rise gently from the plains like half-formed bubbles frozen in time, while others cluster in fractured patches where the crust seems to have blistered and sagged. These aren't just inactive, they're cryptic, as if the planet scrubbed away the very clues that would explain them. Take the enigma of Pantheon Fossae, a sprawling network of troughs radiating from a central point like cracks on a shattered windshield. At its heart lies a peculiar depression, possibly a collapsed volcanic vent, yet satellite images reveal no lava plains or volcanic ash, just an eerie emptiness where fiery outpourings should have left their mark. Contrast this with Hawaii's Kilauea, where rivers of molten rock carve undeniable signatures across the landscape. Mercury's eruptions, it seems, played by different rules, perhaps expelling lava so thin and fast it vanished without a trace, or erupting explosively with gases that left no solid residue. Scientists face a double mystery here. First, why are Mercury's volcanic relics so faint compared to other worlds? One theory suggests the planet's lack of atmosphere allowed lava to disperse as fine sprays, scattering into space before settling. Another proposes that Mercury's lava was unusually fluid, spreading paper thin across vast distances and eroding over billions of years under relentless solar bombardment. But the deeper puzzle is why some regions show clear volcanic Chinese letter like the sprawling plains smoothed by ancient lava floods, while these ghostly structures refuse to fit the mold. Perhaps most intriguing is the possibility that Mercury's volcanism wasn't driven by the same forces as Earth's. Our planet's eruptions stem from tectonic plate movement and mantle plumes, but Mercury's single, unbroken crust may have hosted a stranger breed of volcanism, fueled by the shrinking of its massive core as it cooled, cracking the surface and squeezing out magma like toothpaste from a crumpled tube. Some of these ghost volcanoes might even be failed vents, where lava never quite breached the surface, leaving only swollen mounds as cryptic monuments to what might have been. What makes these features so compelling isn't just their obscurity, it's what they imply about planetary evolution. If volcanoes can leave such ambiguous traces on a world like Mercury, might other rocky planets hide similar secrets in plain sight? As we study these spectral landforms, we're not just piecing together one planet's history, we're learning how volcanic storytelling changes when the stage lacks air, water, and time's usual erosion. Mercury's ghost volcanoes stand as silent witnesses to eruptions we're only beginning to decipher, their stories written in gaps and absences rather than flows and ash. Stretching across Mercury's sun-blasted plains like shadowy fingerprints, patches of an enigmatic dark material cling to the planet's surface, defying straightforward explanation. This isn't ordinary planetary dust or volcanic ash. Spectral analysis reveals it absorbs light far more efficiently than Mercury's typical grayish bedrock, appearing almost inky black against the brighter terrain. Some deposits sprawl across crater floors, while others coat the bases of towering cliffs, their distribution so uneven that scientists initially doubted their own instruments. How could something so visually striking remain chemically ambiguous decades after its discovery? The answer may lie in two competing theories, each more fascinating than the last. The first hypothesis points to the cosmos' ultimate delivery service comets. Carbon-rich cometary fragments bombarding Mercury over eons could have left behind layers of organic compounds, slowly darkening certain regions through accumulated cosmic graffiti. Picture a snowplow spreading salt on winter roads, except here it's cometary snow depositing tar like residues across random planetary patches. Messenger spacecraft data lends credence to this idea, revealing the dark material often correlates with impact sites, particularly around larger craters where volatile-rich projectiles might have vaporized upon hitting Mercury's furnace-like surface. Yet this doesn't fully explain why some similarly sized craters lack the dark coating entirely, or why certain deposits appear concentrated along geological fault lines rather than impact zones. That inconsistency fuels the second, more radical theory. Mercury might be shedding this darkness from within. Before the planet's crust fully solidified, its primordial magma ocean could have hosted vast graphite deposits, essentially floating layers of pure carbon that rose like scum on a cooling pond. As Mercury's surface contracted over billions of years, These ancient carbon veins might have been exposed through cracks and fissures, creating the patchy dark stains we observe today. Supporting this notion are recent measurements showing the material's spectral signature bears eerie similarities to graphite, the crystalline form of carbon used in pencil leads. If confirmed, this would mean we're looking at fragments of Mercury's earliest chemistry, a time capsule from when the planet was literally writing its own history in carbon. What makes this mystery particularly tantalizing is how it challenges our understanding of planetary surfaces. On airless worlds like our moon, space weathering typically brightens terrain over time as solar radiation breaks down minerals into finer, more reflective dust. Mercury's dark patches invert that expectation, growing darker with age in certain locations. Some researchers speculate this could involve complex interactions between carbon compounds and Mercury's intense solar wind environment, creating a self-replenishing cycle of chemical darkening. Others suggest micrometeorite impacts might be gardening the surface, mixing ancient carbon layers with fresh ejecta in unpredictable ways. The implications stretch far beyond academic curiosity. If the material proves to be cometary in origin, it could reveal new details about how volatile elements spread through the inner solar system. If it's endogenous graphite, we may need to revise our models of how metallic elements separate during planetary formation. Future missions equipped with advanced spectrometers could settle the debate, but for now, Mercury's Inkai stains remain one of planetary science's most evocative riddles. A cosmic Rorschach test where every interpretation reveals something profound about our solar system's hidden history. Mercury's surface tells a story of planetary shrinkage written in cliffs that spiral across its landscape like the wrinkles of a raisin. These towering tectonic scars, called lobate scarps, slash hundreds of miles across the planet's crust, some rising over a mile-high, testaments to a world that's been slowly collapsing inward for billions of years. Unlike Earth's jagged fault lines, these formations curve smoothly, their steep faces resembling the toe of an enormous boot pressing into soft clay. Their presence alone isn't shocking planets cool and contract over time, but the scale of Mercury's shrinkage defies all predictions. If these scarps are measuring tapes of planetary compression, then Mercury's tape reads numbers no scientist anticipated. The math is staggering. By measuring the vertical displacement of these scarps, essentially how much one side of the fault has been thrust over the other, researchers calculated Mercury's radius has shrunk by as much as 8 miles since its formation. That might not sound dramatic until you compare it to Earth, which has compressed a mere half-mile over the same period despite being 4 times wider. Even Mars, with its massive volcanoes and ancient tectonic activity, shows no comparable global contraction. But here's where the paradox sharpens. Thermal models of Mercury's evolution, based on its composition and size, predicted only about half the shrinkage we observe. Either Mercury lost heat far faster than physics allows, or our understanding of planetary cooling is missing a critical piece of the puzzle. One radical theory points to Mercury's oversized core as the culprit. As the iron-rich core cooled and solidified, it wouldn't just contract, it would undergo a phase change, reorganizing its crystalline structure in a way that amplifies shrinkage. Picture an ice cube cracking as it freezes, but on a planetary scale. This process, called core precipitation, could have squeezed Mercury's crust like a fist around a stress ball, creating more scarps than gradual cooling alone would explain. Messenger mission data adds weight to this idea, revealing that lobate scarps aren't randomly scattered but clustered in patterns that suggest coordinated stress from below. But there's a counter-argument. Perhaps Mercury's crust itself behaves differently than we assumed. Most models treat planetary crusts as monolithic slabs, but what if Mercury's surface was riddled with weak zones, pre-existing fractures from ancient impacts or volcanic activity, that focused contraction into dramatic scarps instead of distributing it evenly? Recent high-resolution images reveal smaller, previously overlooked scarps crisscrossing even the youngest terrains, hinting that shrinkage didn't just happen in Mercury's distant past but might still be creeping forward today. The implications ripple far beyond academic debates. If Mercury cooled faster than physics predicts, what does that mean for exoplanets orbiting close to their stars? Could there be whole classes of hyper-contracted worlds we've failed to imagine? And if core precipitation or crustal weaknesses explain the discrepancy, does that rewrite the rules for how rocky planets age? Every crease on Mercury's surface is a line in a cosmic mystery novel, one where the final chapter might just redefine how planets' lives shrink and die. Deep within Mercury's polar craters, where perpetual shadows hide ancient ice, astronomers have detected something even more unexpected: brilliant radar reflections so intense they defy conventional explanation. These anomalous bright spots, first noticed during Earth-based radar surveys in the 1990s, ping back radar signals with almost mirror-like efficiency, suggesting the presence of highly reflective materials unlike anything found elsewhere on the planet. At first glance, the obvious suspect would be the water ice deposits we've already discovered, but here's the twist. These reflections shine far brighter than ice ever should, and they appear in locations where no ice could possibly survive. The leading hypothesis points to metallic compounds lurking beneath Mercury's surface, specifically layers of iron, nickel, or even exotic alloys like iron sulfides that could scatter radar waves with unusual intensity. Picture sunlight glinting off a freshly polished car hood. These metallic deposits might be doing something similar with radar beams, creating localized flashes that outshine their surroundings. Some researchers suggest these metals could be remnants of ancient asteroid impacts, where heavy metallic cores from vaporized projectiles rained back down and settled in patches across Mercury's poles. Others propose they're native to Mercury itself, concentrated veins of minerals left behind as the planet's magma ocean cooled and differentiated billions of years ago. Yet not everyone is convinced. Alternative explanations range from the plausible to the borderline fantastical. One camp argues the reflections could stem from instrumental quirks, false positives created by radar waves bouncing off unusually textured terrain at just the right angle to produce a deceptive glare. It wouldn't be the first time planetary science was fooled by an illusion. Similar bright spots on the Moon turned out to be nothing more than rough terrain scattering radio waves in unexpected ways. Another fringe theory suggests the reflections might come from superconducting materials, exotic compounds that, under Mercury's extreme temperature swings, could exhibit bizarre electromagnetic properties. While there's no direct evidence for this, it's a tantalizing possibility that underscores how little we truly understand about the materials hiding in our cosmic backyard. The mystery deepens when comparing these radar anomalies to similar features elsewhere in the solar system. Mars' polar caps produce bright radar returns, but those are neatly explained by thick layers of carbon dioxide ice. Saturn's moon Titan shows reflective patches too, but they're linked to methane lakes. Mercury's bright spots share no clear kinship with these. They're outliers, existing in a thermal environment that should preclude most volatile materials while simultaneously being too intense for simple metallic explanations. Recent data from the Messenger mission added another layer of intrigue. Some of these reflective zones coincide with Mercury's mysterious hollows, those ghostly depressions we explored earlier. Could there be a connection? Are we seeing some kind of volatile metallic hybrid material eroding in ways we've never witnessed before? What makes these reflections so compelling isn't just their scientific puzzle, it's what they represent for future exploration. If confirmed as metallic deposits, they could rewrite our understanding of Mercury's geological diversity. If they're instrumental artifacts, they force us to re-examine decades of planetary radar data with fresh skepticism. And if there's something truly unexpected, Well, that's the thrill of Mercury, a world that continually serves up mysteries where we least anticipate them. Until a rover or lander can physically scrutinize these gleaming enigmas, they'll remain one of the solar system's most intriguing maybes, a reminder that sometimes the universe's quietest signals carry the loudest questions. Mercury's surface chemistry reads like a cosmic crime scene, a puzzling absence where key elements should be. Volatile substances like sulfur, potassium, and sodium, common on other rocky worlds, are conspicuously scarce across much of Mercury's sun-baked terrain. This depletion defies basic planetary logic. These elements aren't rare in the solar system, and Mercury's violent bombardment history should have delivered plenty. Yet spectral analysis reveals vast regions where volatiles are nearly absent, as if someone or something scrubbed them from the geological record, the prime suspect. Our own star, solar wind stripping, offers the most straightforward explanation. Mercury orbits so close to the Sun that it's bombarded by charged particles streaming from its fiery surface at over 1 million miles per hour. These particles act like a cosmic sandblaster, knocking loose volatile atoms and hurling them into space. The process isn't gentle, it's a relentless, eons-long assault that could strip away entire layers of vulnerable elements. Imagine standing in a hurricane with a handful of powdered sugar. Mercury's volatiles face similar odds. Supporting this theory are laboratory simulations showing how solar wind can sputter light elements off mineral surfaces, leaving behind only the most stubborn materials. But the plot twists when we examine Mercury's so-called hollows, those eerie, bright floor depressions we explored earlier. These features are bizarrely rich in sulfur and chlorine, elements that should have been the first to vanish under solar bombardment. It's as if Mercury hid reserves of volatiles in plain sight, tucked away in geological safes that even the Sun couldn't crack. One explanation suggests these pockets might be recent exposures, where fresh material was uncovered by impacts or shifting crust before solar wind could erode it. Another, more tantalizing idea proposes that Mercury's interior periodically releases volatile-rich vapors through cracks, replenishing surface deposits like a planetary-scale geyser system. The Messenger spacecraft uncovered yet another wrinkle. Mercury's polar regions show unexpected potassium-to-thorium ratios, a chemical signature that shouldn't exist if solar wind stripping worked as efficiently as models predict. This discrepancy hints at complex, localized processes. Perhaps some volatiles are being recycled between surface and exosphere, or certain minerals are shielding vulnerable elements like cosmic bunkers. Even stranger, these anomalies often correlate with magnetic bubbles in Mercury's miniature magnetosphere, suggesting the planet's patchy magnetic field might create temporary safe zones where volatiles can linger. What makes this mystery so compelling is its implications for exoplanet science. If a planet as close to its star as Mercury can preserve volatile reservoirs against all odds, how many other worlds might hide similar surprises? Future missions armed with advanced spectrometers could finally crack this case, but for now, Mercury's missing volatiles stand as a testament to nature's stubborn refusal to follow neat theoretical rules, proving once again that the universe keeps its most fascinating secrets in the gaps between our expectations and reality. The Caloris Basin isn't just Mercury's largest impact crater, it's a geological oddity that looks like it was carved with a cosmic chisel. Stretching nearly 1,000 miles across, this colossal scar should be a textbook example of a circular impact basin, similar to the Moon's familiar Maria. But peer closer and its edges defy expectations. Instead of smooth curves, Caloris sports jagged, polygonal borders, as if some unseen force cracked the planet's crust along precise geometric lines before the impact even occurred. Even stranger, its interior is etched with concentric rings like ripples frozen in stone, a feature seen nowhere else in the solar system at this scale. These aren't just quirks of formation, they're clues to Mercury's hidden vulnerabilities, written in planetary braille. The polygon's sharp angles suggest Mercury's crust was pre-fractured before the calamitous collision that created Caloris. Picture dropping a hammer onto a sheet of ice already laced with hairline cracks. The impact wouldn't create a neat circular hole, but instead follow the existing weaknesses, shattering the surface along its hidden fault lines. This implies Mercury's early crust was crisscrossed with tectonic stresses, possibly from the planet's rapid cooling or the gravitational tug of war with the Sun. Some researchers argue these fractures might trace back to Mercury's great shrinkage, when the planet's contracting crust split like the skin of a drying fruit. Others propose they're relics of even older cataclysms, perhaps remnants of a gargantuan impact that nearly tore Mercury apart long before Caloris was born. Then there are the rings, most large impact basins in the solar system, like the Moon's Oriental feature, rugged mountain peaks circling the central depression, formed when the surface rebounded after the asteroid struck. But Caloris rings are different, smoother, more regular, almost like tree rings preserving the aftermath of the impact in eerie detail. One theory suggests Mercury's thin crust and massive iron core acted like a drumhead during the collision, vibrating in ways that left these precise concentric patterns. Another possibility involves the impactor itself, a rare oblique strike at just the right angle to send shockwaves rippling outward in perfect symmetry. Or perhaps Mercury's unique surface materials responded to the energy of the hit differently than other worlds, creating rings where others would form peaks. The debate takes a speculative turn when considering Caloris' antipodal counterpart, the chaotic terrain we explored earlier. Some models suggest the impact was so violent it sent seismic waves racing through Mercury's core, converging on the opposite side with enough force to scramble the landscape like a planetary-scale earthquake. If true, Caloris' strange shape might not just reflect local crustal weaknesses but global reverberations, an echo of the planet's entire structural integrity being tested in an instant. What makes this mystery so pivotal is what it reveals about planetary scars in general. If Caloris' form was shaped by pre-existing fractures, then giant impacts might not just create chaos, they could also expose a world's hidden architectural flaws. Future missions mapping Mercury's gravity field in detail might finally settle the debate, but for now, Caloris stands as a monumental riddle. A crater that didn't just hit Mercury but revealed its deepest cracks, both literal and metaphorical. Scattered across Mercury's sun-scorched plains lie patches of ground so dazzlingly bright they seem to defy the planet's otherwise muted palette. These high-albedo regions, named for their uncanny ability to reflect sunlight, glow like beacons against the dark basalt plains, yet they're neither hollows nor polar ice deposits. Some appear as faint smudges no larger than a city block, while others stretch for miles, their borders sharp as knife cuts against the surrounding terrain. What makes them even more perplexing is their distribution. They cluster in areas with no obvious geological significance, as if someone sprinkled flecks of celestial glitter at random. Radar observations reveal these patches reflect not just visible light but radio waves too, a rare dual signature that points to something far stranger than ordinary rock. One leading theory suggests these bright spots could be fresh impact ejecta pulverized material flung outward by recent meteor strikes. When a space rock slams into Mercury's surface, it digs up deeper layers of crust that haven't been darkened by billions of years of solar wind exposure. Think of it like scratching the paint off an old car to reveal shiny metal underneath. This would explain why some bright patches radiate from small, young craters, their rays resembling sunbursts frozen in time. But there's a problem. Not all high albedo zones match this pattern. Some sit isolated in ancient terrain, far from any obvious impact, while others appear suspiciously aligned with tectonic fractures or volcanic vents, hinting at alternative origins. Mineralogical oddities offer another compelling explanation. Spectral data from the Messenger mission detected unusually high concentrations of feldspar, a light-colored mineral, in some bright regions. On Earth, feldspar gives granite its sparkle, but on Mercury, it might form vast, reflective deposits through processes we've yet to understand. One provocative idea posits that volcanic gases could have deposited feldspar-rich coatings like crystalline frost across certain areas. Alternatively, the planet's extreme temperature swings might be physically weathering surface rocks, breaking them down into finer, more reflective grains over time, a phenomenon seen in lab simulations but never confirmed on a planetary scale. The wild card in this mystery is Mercury's unique space environment. Unlike the Moon, which has a relatively stable surface, Mercury endures constant bombardment not just from micrometeorites but from the Sun's relentless particle storms. Some scientists speculate these high albedo patches might be temporary features, fresh debris fields that darken within centuries under solar wind sputtering, only to be renewed by subsequent impact. This could explain why some bright areas appear crisper than others, as if caught in different stages of an invisible fading process. Perhaps the most tantalizing clue comes from comparing these patches to similar features elsewhere. Mars has its own bright spots, often linked to salt deposits or frost. Jupiter's moon Europa sports reflective ice plains, but Mercury's versions share little in common with these. They're neither icy nor salty, yet they shine just as brilliantly. This suggests we might be looking at an entirely new class of planetary surface phenomenon, one that could rewrite our understanding of how airless worlds evolve under extreme conditions. Until future missions can sample these gleaming anomalies directly, they'll remain one of Mercury's most visually striking riddles, a reminder that even in the starkest landscapes, the universe paints with unexpected light. Mercury wears a comet's disguise, a wispy, glowing tail of sodium atoms stretching millions of miles into space, as if the planet is trying to escape its own orbit. This ethereal feature, invisible to the naked eye but striking in specialized telescopes, billows opposite the Sun like a cosmic windsock caught in a stellar breeze. Unlike the dusty tails of comets, Mercury's appendage consists entirely of sodium atoms, a delicate stream of particles torn from the planet's surface and hurled into the void by the Sun's relentless fury. What makes this phenomenon even stranger is its fickleness. The tail's brightness can surge or fade by a factor of 10 in just days, pulsing unpredictably like the heartbeat of a hidden cosmic clock. The physics behind this celestial spectacle are both elegant and violent. Solar radiation and micrometeorites constantly pummel Mercury's surface, kicking sodium atoms loose from minerals in its crust. These liberated particles get swept up by photons, individual particles of sunlight, which push them outward with enough force to overcome Mercury's weak gravity. Picture a beach where every grain of sand is suddenly launched skyward by invisible waves, forming a shimmering cloud that trails downwind. But here's where the mystery deepens. Simple radiation pressure can't explain the tail's extreme variability. On some observations, it shines as bright as a dim comet. On others, it nearly vanishes from detection. Solar activity plays a role, but not in the way scientists expected. During periods of heightened solar wind, when charged particles stream from the Sun at increased speeds, Mercury's tail often dims, the opposite of what you'd assume if solar wind were the primary driver. Instead, researchers suspect magnetic fields are stirring the pot. Mercury's miniature magnetosphere, though weak, may act like a chaotic filter, sometimes funneling sodium atoms into concentrated jets and other times scattering them into diffuse clouds. Earth-based telescopes have caught the tail performing outright gymnastics, kinking, splitting, or even forming temporary secondary streams, as if unseen forces are playing tug-of-war with its structure. The wild card in this puzzle is Mercury's exosphere, an ultra-thin shroud of gases clinging to the planet's surface. Unlike proper atmospheres, exospheres don't have enough molecules to bounce into each other, meaning every sodium atom follows its own independent trajectory. Some get launched straight into the tail, while others ricochet along unpredictable paths, creating a dynamic, ever-changing reservoir of particles. Add Mercury's eccentric orbit, which brings it alternately closer and farther from the Sun, and you have a recipe for cosmic mood swings. When the planet swings nearest the Sun, temperatures on its day side spike, potentially vaporizing fresh sodium from surface minerals and supercharging the tail. Weeks later, as Mercury retreats, the spigot might partially close. What makes Mercury's sodium tail so much more than a pretty light show are the implications for other worlds. If an airless, sun-blasted rock can maintain such a dynamic exospheric feature, what might lurk around similarly extreme exoplanets? Future missions could use sodium tails as diagnostic tools, revealing surface composition and magnetic properties from light years away. For now, though, this flickering ribbon of atoms remains one of Mercury's most poetic mysteries, a celestial scarf woven from sunlight, magnetism, and the whispers of a planet slowly giving itself away to space. At the heart of Mercury's vast Caloris Basin lies one of the most striking geological oddities in our solar system, a feature so bizarre it's earned the nickname the Spider. Officially known as Pantheon Fossae, this sprawling network of troughs radiates outward from a central point like cracks in a shattered windowpane, stretching over 100 miles across the planet's surface. But what makes this formation truly uncanny isn't just its appearance, it's the fact that nothing like it exists anywhere else we've explored. Most radial fracture systems on other worlds trace back to meteor impacts where shockwaves blast outward in perfect symmetry. The Spider defies that template, its fractures too precise, too orderly, and too intimately tied to volcanic forces to fit the impact mold. The central mystery here is one of origins. Some planetary scientists argue the Spider's fractures were born from volcanic fury specifically, a massive magma chamber that bulged upward, stretching the surface until it split like overripe fruit. Evidence for this lies in the trough's clean, sharp edges and their convergence on a central depression, reminiscent of lava domes on Earth that collapse under their own weight. Others point to the sheer scale of the fractures, some over a mile wide, as proof of something more explosive. Perhaps a subterranean gas pocket detonated with enough force to rupture the crust in this eerie radial pattern. Either way, the result is a geological masterpiece that looks more like abstract art than natural formation. What sets the Spider apart from any other radial feature in the solar system is its hybrid nature. Mars has its own fracture systems, like the sprawling Cerberus fossae, but those are linear cracks caused by tectonic stretching. The Moon's Tycho crater boasts brilliant rays, but those are surface debris ejected by an impact. The Spider, by contrast, seems to blend volcanic and tectonic processes in a way that challenges categorization. Messenger spacecraft data reveals another twist: the troughs aren't empty. Some are lined with reflective deposits that might be volcanic minerals or even sublimated volatile compounds, suggesting the fractures served as conduits for subsurface materials to reach the surface. The plot thickens when you consider the Spider's relationship to the Caloris Basin itself. Located almost dead center within this colossal impact scar, the fractures might be exploiting weaknesses left by the basin's formation, like cracks spreading through a car windshield from a single chip. But if that's true, why don't we see similar features in other large impact basins across the solar system? One tantalizing possibility is that Mercury's unique composition, its oversized core and thin crust, created the perfect conditions for this one-of-a-kind structure. The planet's iron-rich interior may have contracted unevenly as it cooled, putting the crust under extraordinary stress. Add the titanic energy of the Caloris impact, and you have a recipe for geological chaos that sculpted something utterly singular. Perhaps the most haunting question the Spider poses isn't how it formed, but why we've found nothing like it elsewhere. Is this a fluke of Mercury's violent history, or a sign that we've underestimated the diversity of planetary geology? Future missions might drill into those luminous troughs, searching for answers in their depths. Until then, the spider remains a silent enigma, a reminder that even in a universe of infinite repetition, some things refuse to conform. Mercury's magnetic field doesn't just deflect solar wind, it tangles with it in a savage celestial dance, twisting into shapes so violent they've earned the name magnetic tornadoes. Near the planet's poles, spacecraft have detected spiraling columns of magnetic energy, each one a whirling vortex where the sun's charged particles get sucked into Mercury's magnetosphere like leaves caught in a storm. These aren't harmless swirls, they're plasma-filled funnels powerful enough to rip atoms straight from Mercury's already wispy exosphere, flinging them into space at staggering speeds. Imagine a cosmic vacuum cleaner running non-stop on a planetary scale, stealing what little atmosphere Mercury struggles to hold onto. What makes these tornadoes so baffling is their hybrid nature, part magnetic, part electric, wholly unpredictable. Earth's auroras create similar but gentler spirals near our poles, where solar wind particles slide along orderly magnetic field lines. Mercury's versions are chaotic by comparison, their magnetic lines kinking and braiding like overwound rubber bands. Messenger spacecraft data revealed their secret. These tornadoes form when Mercury's weak magnetic field gets pressed flush against the planet's surface by intense solar wind, creating unstable pockets where magnetic energy erupts in frantic loops. The result is a particle accelerator in nature's laboratory, where electrons and ions get spun to violent speeds before being ejected entirely. The real shock came when scientists calculated the atmospheric toll. A single large magnetic tornado might strip away more exospheric particles in an hour than solar wind erodes in days. This explains a long-standing puzzle: why Mercury's sodium and oxygen exospheres flicker so dramatically over short timescales. It's not just solar radiation baking atoms off the surface. It's these invisible whirlwinds yanking them away by the millions. Some researchers suspect the tornadoes might even contribute to Mercury's bizarre tale of escaping sodium atoms, acting as particle cannons that fire material downwind. Yet for all their destructive power, magnetic tornadoes might also be Mercury's unlikely protectors. By channeling solar wind particles into concentrated columns, they prevent more widespread erosion across the planet's dayside. It's a paradoxical balance: localized violence that spares the greater whole, like a lightning rod drawing fire away from a building. Future missions like BP Colombo could finally untangle their full role, but for now, these whirling dervishes of magnetism remain one of Mercury's most dynamic mysteries. A reminder that even in the quietest corners of space, invisible storms rage on. Mercury's surface chemistry holds a glaring contradiction that has planetary scientists questioning decades of assumptions. Potassium, an element that should have vanished under the planet's blistering conditions, persists in quantities that defy all expectations. This isn't just a minor discrepancy, it's a direct challenge to our understanding of how rocky worlds form close to stars. Potassium is a volatile element, meaning it vaporizes easily under heat, and Mercury's proximity to the Sun should have baked it away like steam from a boiling pot. Yet spectral data from the Messenger spacecraft revealed potassium levels up to 10 times higher than predicted, lurking in Mercury's rocks like a stubborn guest refusing to leave the party. The implications ripple far beyond a single element's abundance. Current models of planetary formation suggest Mercury either endured temperatures so extreme during its birth that most volatiles boiled off, or it formed from rare, metal-rich precursor materials that lacked volatiles altogether. Both scenarios predict a potassium-depleted surface, yet Mercury flips the script entirely. One radical theory proposes that potassium might have hitchhiked to Mercury aboard sulfur-rich minerals, which could have acted as cosmic bodyguards, shielding the volatile element from solar heat long enough to embed it in the crust. Picture a fragile ice cube surviving a desert trek because it's trapped inside an insulated thermos. Sulfur's chemical bonds might have provided similar protection during Mercury's fiery infancy. Another possibility rewinds the clock to the solar system's chaotic early days. If Mercury formed farther from the Sun before migrating inward, it could have accumulated potassium-rich materials in cooler regions, preserving them even as the planet later moved into its scorching present orbit. This would explain not just the potassium but also Mercury's puzzling sulfur excess, a duo of volatiles that shouldn't coexist so close to the Sun. Supporting this idea are dynamic simulations showing how gravitational tugs from Jupiter or Saturn could have nudged Mercury into its current position, though conclusive evidence remains elusive. The plot thickens when comparing Mercury to other rocky bodies. The Moon, despite being smaller and cooler, has far less potassium, while Mars, often considered a volatile-rich world, shows proportions closer to Earth's. This inconsistency suggests Mercury's potassium isn't just a fluke but a clue to unique processes we've yet to account for. Some researchers speculate that Mercury's magnetic field, weak as it is, might have played a role in trapping potassium ions from the solar wind, slowly enriching the surface over eons. Others point to the planet's massive core, whose cooling could have released potassium-rich fluids through cracks in the crust, like a planetary-scale geyser system. What makes this mystery so pivotal is its potential to rewrite the rules of planetary chemistry. If potassium can survive such extreme conditions, what other volatiles might be hiding in plain sight on seemingly inhospitable worlds? Future missions carrying advanced spectrometers could settle the debate, but for now, Mercury's stubborn potassium stands as a testament to nature's refusal to conform to tidy models, a reminder that the universe often keeps its most profound lessons tucked inside the exceptions. Among Mercury's countless impact scars, a handful stand out like cosmic bull-sized craters with not one, but two perfectly concentric rings rising from their floors like frozen tidal waves in stone. These double-ringed anomalies defy the typical bowl-shaped simplicity of most impacts, their intricate structure hinting at violent celestial collisions playing out under rules we're only beginning to decipher. Take the stunning example of Caloris Basin, a 75-mile-wide pit with an inner ring so crisp it looks freshly chiseled, surrounded by an outer rampart half again as wide. Such formations are vanishingly rare elsewhere in the solar system. Even the Moon's grandest impact basins only achieve multiple rings at scales 10 times larger. How could Mercury, a world barely bigger than our Moon, produce these miniature masterpieces of destruction? The secret may lie in what happens when an asteroid strikes Mercury's unique crust at just the right speed and angle. Most craters form when impactors punch straight through the surface, excavating material in a single explosive rebound. But double rings require something subtler, a glancing blow where the initial collapse of the transient crater triggers a secondary upheaval, like a pebble dropped into wet sand creating concentric ripples. Computer simulations suggest Mercury's unusually thin crust over its massive iron core might amplify this effect, allowing shockwaves to bounce off the dense interior and sculpt the surface with eerie precision. Imagine slapping a drumhead with your palm. The initial impact creates a dent, but the recoil from the drum's frame makes the skin ripple outward in perfect circles. Mercury's core could be playing that same role on a planetary scale, yet speed matters just as much as structure. Lunar double-ring basins like Oriental were carved by relatively slow-moving projectiles, cosmic leftovers from the solar system's chaotic infancy. Mercury's versions, by contrast, might owe their existence to hypervelocity impacts, where asteroids accelerated by the Sun's gravity strike at speeds exceeding 30 miles per second. At such extremes, the energy release becomes almost nuclear, vaporizing not just the impactor but entire layers of Mercury's surface. The resulting shockwaves could interact with subsurface mineral seams or ancient lava tubes, creating zones of weakness where the second ring preferentially forms. Some double-ringed craters even show strange grooved terrain between their rings, as if the ground momentarily turned to liquid before refreezing in these bizarre patterns. What makes these formations truly mystifying is their apparent youth. Radiatladi's inner floor gleams with an almost metallic sheen in spacecraft images, its minimal cratering suggesting it might be less than 1 billion years old, a blink in geological time. This raises a provocative question. Is Mercury still experiencing impacts energetic enough to create new double-ringed craters today? Or are we seeing the last remnants of a bygone era when the inner solar system was far more crowded with high-speed debris? The implications stretch far beyond academic curiosity. If double rings require specific crustal thicknesses or impact velocities, they could serve as cosmic speedometers, allowing us to clock ancient collision rates across the solar system. Future missions might drill into these peculiar basins, searching for mineral clues locked in their concentric embrace. Until then, Mercury's twin-ringed craters remain both artwork and enigma, their perfect circles holding secrets of violence and beauty written in planetary flesh. Amid Mercury's monotonous gray landscape, certain craters glow with an otherworldly blue tint, splotches of color so vivid they seem digitally altered. These blue halo craters stand out like sapphires scattered across charcoal, their spectral signatures revealing mineral cocktails unlike anything on the surrounding plains. While most of Mercury's surface reflects sunlight with dull, uniform efficiency, these anomalies absorb red and infrared wavelengths, giving them an eerie cerulean hue in enhanced color images from the Messenger spacecraft. The culprit, likely ilmenite, a titanium iron oxide mineral that's jet black in your hand but plays tricks with light when scattered across planetary surfaces. What makes these craters particularly fascinating is their tie to Mercury's violent past. The blue halos often correlate with fresh impact sites, where asteroids punch deep enough to excavate material from beneath the planet's weathered crust. Picture a shovel striking a layered cake. The deeper the blade goes, the brighter and more colorful the exposed layers become. In Mercury's case, ilmenite-rich deposits from the planet's volcanic heyday may have been buried under eons of solar wind-darkened debris, only to resurface in these brilliant ejecta blankets. Some halos even show glassy, impact-melted edges, beads of once molten rock that cooled so fast they trapped their unusual chemistry in translucent snapshots. But there's a twist. Not all blue halos are created equal. Some appear around small, youthful craters, suggesting recent impacts tapped into shallow ilmenite veins. Others encircle ancient basins, their colors muted but widespread, hinting at epochs when Mercury's volcanic fires belched titanium-rich lavas across vast regions. The most perplexing examples straddle the line between crater and volcanic vent, like the enigmatic Navoy crater, where blue-toned fractures radiate outward as if mineral-rich gases once seeped through the cracks. This overlap raises a tantalizing question. Could some halos be signatures of extinct geothermal activity rather than impact debris? The Messenger mission added fuel to the debate by detecting unusual chlorine concentrations in several blue halo zones, a fingerprint of volatile elements that shouldn't survive Mercury's solar broiling. One radical theory suggests these craters might be time capsule sites where reactive titanium minerals chemically trapped volatiles from Mercury's early, more atmosphere-rich days, preserving them like cosmic amber. If true, future landers could dig into these colorful patches and taste whispers of the planet's lost adolescence. What makes these azure anomalies more than just visual curiosities is their potential to rewrite Mercury's geological resume. On the Moon, similar blue tints mark regions rich in helium-3, a prized resource for fusion energy. Could Mercury's halos harbor their own surprises? From ilmenite-fueled solar wind interactions to cryptic volatile reservoirs, these craters prove that even in a realm of extremes, nature keeps a palette of secrets painted in shades no one expected. Mercury's surface hides cryptic formations that look more like celestial dotted lines than natural geology, long chains of perfectly aligned pits. each one a sunken void with no apparent connection to the volcanic tunnels or impact fractures we see elsewhere in the solar system. These pit chains, some stretching for hundreds of miles, resemble sinkholes drilled by an invisible cosmic seamstress, their edges sharp and their bottoms lost in shadow. Unlike the skylights of collapsed lava tubes found on Mars or the Moon, these pits show no signs of volcanic activity nearby. Instead, they trace subtle fault lines across Mercury's crust like stitches holding the planet together or perhaps unraveling it. The leading explanation for these eerie alignments points to subterranean gases making a violent escape. As Mercury's core cooled and contracted over billions of years, its shrinking crust may have opened deep fissures, releasing pockets of trapped volatiles, sulfur dioxide, carbon monoxide, or even water vapor that had been locked beneath the surface since the planet's fiery youth. Imagine uncorking a champagne bottle underwater, watching bubbles rush upward in a frantic column. On Mercury, these gases might have exploded through fractures, undermining the ground above and triggering sequential collapses that left behind these haunting pit chains. Messenger spacecraft data lends weight to this theory, showing elevated sulfur levels around some pits, as if the ground itself exhaled its secrets before sealing them in these sunken vaults. Yet there's a competing hypothesis even more tantalizing. These pits could mark the graves of ancient subsurface voids, caverns carved not by lava, but by some forgotten geological process unique to Mercury. On Earth, limestone caves dissolve slowly under acidic groundwater, but Mercury has no water to speak of. Instead, these voids might have formed during the planet's chaotic early days when its crust was still hot enough to deform like taffy. As magma retreated or minerals crystallized at depth, hollow spaces could have formed like bubbles in cooling cement, only to collapse later under the weight of shifting crust. Some pit chains even curved gently, following the arc of hidden faults, suggesting Mercury's interior might be riddled with a honeycomb of such voids waiting to be discovered. The mystery intensifies when considering the pit's uncanny preservation. Mercury's surface is constantly sandblasted by micrometeorites and solar radiation, yet many pit chains show minimal erosion, their crisp edges defying billions of years of abuse. This could mean there's surprisingly young evidence that Mercury's interior might still be venting gases or shifting today. Alternatively, their resilience might hint at an unknown material property, perhaps a mineral cement that hardened the pit walls against erosion. Either way, these formations act as eerie time capsules, preserving snapshots of processes we've never witnessed directly. What makes these pit chains more than just geological curiosities is their potential to reveal Mercury's hidden volatile inventory. If gases are indeed responsible, they could point to vast underground reservoirs of elements we assumed the planet had lost long ago. Future missions equipped with ground-penetrating radar might finally peer beneath these pits, uncovering whether they're mere scars or the mouths of sprawling subterranean labyrinths. Until then, these sunken corridors remain silent witnesses to a Mercury we're only beginning to fathom, a world where even the ground beneath our feet is riddled with enigmas. Mercury plays a cosmic shell game with its temperatures. What should be the hottest place on the planet often isn't where you'd expect. While most worlds bake most intensely at their equators under direct sunlight, Mercury's hot poles shift like desert mirages, sometimes appearing dozens of degrees warmer in regions that technically receive less solar radiation. This thermal quirk stems from two of the planet's strangest traits: its wildly elliptical orbit and the bizarre way its surface stores and releases heat. Imagine holding a cast iron skillet over a campfire. Even after moving it away from the flames, the metal stays scalding for minutes, a property called thermal inertia. Mercury's surface behaves similarly, but with a dramatic twist. As the planet swoops closer to the Sun during its eccentric orbit, daytime temperatures at certain longitudes can spike to 800 degrees Fahrenheit. But because Mercury rotates so slowly a single day, there lasts 59 Earth days, these superheated regions linger in sunlight long enough to become thermal batteries, storing absurd amounts of energy in their dense, dry rocks. By the time the planet pivots these zones into darkness, they've absorbed so much heat that they keep radiating it outward even as cooler areas rotate into daylight. The result, hot spots that lag behind the sun's position like overworked engines struggling to cool down. The real surprise comes at perihelion Mercury's closest approach to the sun when orbital dynamics amplify this effect. The planet's uneven speed means some longitudes experience longer afternoons near perihelion, baking under extended solar exposure while other regions get brief, milder heating. Over time, these overworked hotspots settle into two distinct warm poles offset from the equator, creating temperature imbalances that would baffle any weather satellite. Data from NASA, a messenger spacecraft, revealed these thermal anomalies can reach 50 degrees hotter than surrounding areas despite receiving identical sunlight, a disparity comparable to Death Valley's extremes occurring inexplicably in Oregon. But Mercury's thermal tricks don't stop there. The planet's lack of atmosphere removes any buffer for distributing heat, allowing neighboring terrains to develop stark thermal contrast. Darker surfaces absorb more energy while lighter regions reflect it, creating patchwork temperature maps that shift with the seasons. Some impact craters even act as cold traps, their shadows creating localized frost pockets just miles away from scorching plains. This dizzying thermal tapestry hints at complexities we're only beginning to map, where a single degree of longitude can mean the difference between molten lead and freezing shadows. What makes these wandering hot poles more than just celestial trivia is their challenge to planetary climate models. If a world as simple as Mercury, no atmosphere, no oceans, no vegetation, can develop such convoluted temperature patterns, how might exoplanets around volatile stars behave? Future missions equipped with infrared mappers could untangle this riddle, but for now, Mercury's thermal dance remains a masterclass in cosmic thermodynamics, proving even the simplest-looking systems can harbor astonishing depth when you take a closer look. Mercury's exosphere behaves like a ghost fading in and out of existence, an ethereal shroud of atoms so thin that its particles never collide, each one following its own lonely trajectory until solar forces whisk it away. Unlike Earth's thick, protective atmosphere, this wispy veil clings desperately to the planet's surface, constantly bleeding atoms into space in ways that defy prediction. Sodium, oxygen, and hydrogen atoms hop along the surface like cosmic dust bunnies, occasionally launched skyward by solar photons or micrometeorite impacts, only to vanish without warning. What makes this exospheric ballet so baffling isn't just its fragility, it's the way it fluctuates wildly, vanishing and reappearing in cycles that leave scientists scrambling for explanations. Solar storms act as the primary puppeteer in this erratic performance. When the sun erupts with a coronal mass ejection, charged particles slam into Mercury's exosphere like a tidal wave, stripping atoms away at speeds exceeding 100,000 miles per hour. Observations reveal these events can deplete localized patches of sodium, one of the exosphere's key components, by over half in just hours. Yet within days, sometimes mere hours, the missing atoms reappear as though replenished by invisible hands. This seesaw effect suggests hidden reservoirs or resurfacing mechanisms we've yet to map. Picture a sponge being wrung dry, only to mysteriously soak up moisture again the moment no one's looking. But the sun's tantrums only account for part of the mystery. During periods of calm solar weather, when models predict stable exospheric loss, Mercury still surprises us. Ground-based telescopes have caught sodium clouds suddenly brightening over specific regions, notably the planet's magnetically shielded polar dawn zones, before dimming just as abruptly. These spontaneous surges hint at underground processes at work, perhaps volatile rich minerals releasing gases through cracks when heated by sunlight, or even electrostatic forces lofting particles like a planetary-scale static cling. Messenger spacecraft data added another wrinkle. The exosphere's sodium atoms often cluster in comet-like tails streaming away from the Sun, but their direction and intensity shift unpredictably, as if guided by invisible magnetic currents we can't yet trace. Measuring this vanishing act is like trying to weigh smoke with a bathroom scale. Earth-based observations rely on sunlight reflecting off exospheric atoms, but Mercury's proximity to the Sun means it's often lost in the solar glare, visible only during brief twilight windows. Spacecraft measurements face their own hurdles. Messenger's instruments could only sample the exosphere fleetingly during high-speed flybys, leaving gaps in our understanding of its daily rhythms. Even the most advanced simulations struggle to account for Mercury's wild variability, often missing sudden density spikes or drops recorded by observatories. The stakes here are higher than they might seem. If we can crack the code of Mercury's exospheric yo-yo, we might unlock secrets about how other airless worlds like our moon or distant exoplanets orbiting close to their stars lose their atmospheres over time. Future missions like BP Colombo aim to monitor these fluctuations in real time, but for now, Mercury's vanishing exosphere remains one of the solar system's most elusive magic tricks, a celestial puff of smoke that disappears just as you think you've caught it. Among Mercury's ancient cratered skin, vast plains of suspiciously smooth terrain sprawl like fresh pavement on an old road, regions so unblemished they appear decades young in a landscape billions of years old. These lava plains, some spanning areas larger than Texas, bear all the hallmarks of recent volcanic resurfacing: shallow slopes, minimal cratering, and wrinkled ridges that suggest lava once flowed here long after Mercury's violent early history should have ended. The problem, recent, is a loaded term on a planet where most geologic activity supposedly ceased over 3 billion years ago. Yet the evidence stares back at us, crisp and undeniable. These plains look like they solidified yesterday, geologically speaking. The smoking gun lies in their crater counts. Planetary scientists use impact craters like cosmic clocks. The more a surface is pockmarked, the older it's assumed to be. Mercury's smoothest plains, like those surrounding the Rachmaninoff crater, show crater densities up to 10 times lower than their surroundings, implying they might be as young as 1 billion years. That's an eye blink compared to the Moon's dark Maria, which haven't seen fresh lava in over 2 billion years. Some fractured terrains within these plains even resemble cracked mudflats, as if the surface sank slightly after molten rock retreated beneath it, a telltale sign of volcanic withdrawal. But here's where the debate ignites. Volcanism requires internal heat, and Mercury's small size should have lost its furnace like core temperatures eons ago. How could lava still breach the surface so late in the game? One radical theory suggests Mercury's oversized iron core might harbor pockets of radioactive potassium or thorium, elements whose decay could provide unexpected geothermal longevity. Picture a dying campfire with a few stubborn coals buried deep in the ash, still hot enough to reignite dry tinder. Alternatively, tidal friction from the Sun's gravity might have flexed Mercury's interior just enough to squeeze out final volcanic gasps like toothpaste from a nearly empty tube. Impact melt complicates the picture further. When large asteroids strike at planetary scales, the energy released can liquefy local rock, creating temporary lakes of molten material that later solidify into smooth plains. Some researchers argue Mercury's young terrains might be impact melt sheets masquerading as lava flows, a cosmic case of mistaken identity. The distinction matters. Volcanic plains imply sustained internal activity, while impact melt is a one-time surface veneer. Messenger spacecraft data revealed a clue in the mineralogy. These plains are rich in magnesium, a signature often tied to Mercury's deeper mantle, suggesting volcanic origins. But without seismic sensors on the ground, the question simmers unresolved. the most tantalizing possibility, Mercury's volcanic story might not be linear. Instead of a steady decline, the planet could have experienced sporadic, violent outbursts separated by long dormancy, like a geyser field cycling between stillness and eruption. Some smooth plains show overlapping flow fronts, evidence of multiple eruptions, while others exhibit bizarre, ghost craters, where lava partially submerged impact sites like wax sealing a dimpled envelope. These features hint at episodic resurfacing, where Mercury's interior flickered back to life in fits and starts before finally going dark. What makes this mystery more than academic is its challenge to planetary aging. If a small, core-dominated world like Mercury can stay volcanically active longer than physics predicts, what does that mean for exoplanets orbiting red dwarfs or gas giants? Future missions with ground-penetrating radar could settle the debate, but for now, these deceptively youthful plains stand as Mercury's final geologic whisper, a reminder that even in the solar system's senior years, some worlds still have the capacity to surprise. Beneath Mercury's ironclad exterior lies a layer shrouded in cosmic secrecy, a mantle so enigmatic that even our most advanced spacecraft struggle to unveil its composition. Remote sensing instruments, which can typically peer through a planet's crust to analyze deeper layers, meet an unusual obstacle here. Mercury's mantle refuses to betray its secrets, reflecting and scattering signals in ways that defy conventional models. This isn't just a technical hiccup, it's a glaring gap in our understanding of planetary interiors. Why does this layer, which should be a straightforward mix of silicates and metals, behave like a celestial vault locked tight against prying instruments? One prevailing theory suggests Mercury's mantle might be laced with unexpected minerals, exotic compounds forged under conditions unique to the inner solar system. On Earth, the mantle is dominated by olivine and pyroxene, but Mercury's proximity to the Sun could have cooked its subsurface into something stranger. Laboratory experiments hint at the possibility of sulfides, metallic sulfur compounds forming dense, radar-scattering layers under extreme heat and pressure. Picture a planet-sized blacksmith's forge where sulfur-rich vapors permeate molten rock, creating a mantle that's more alloyed toolkit than rocky layer. This could explain why seismic waves from impact seem to slow abruptly as they penetrate deeper, a phenomenon that would make sense if the mantle were peppered with dense metallic pockets acting like speed bumps for vibrations. Another twist comes from Mercury's volcanic history. The planet's smooth plains, formed by ancient lava flows, contain far less iron than typical basalts, suggesting their source magma was oddly depleted in certain elements. If Mercury's mantle was stripped of its iron early on, perhaps by the same colossal impact that blew away much of its crust, what remains might be a skeletal version of what mantles typically look like, rich in refractory minerals like enstatite that survive high temperatures but confound remote sensing. It's as if Mercury's mantle is a ghostly negative of Earth's, shaped by processes so violent they left behind a shadow of what planetary interiors ought to be. The wild card in this puzzle is Mercury's magnetic field. Most planets generate magnetic fields through churning molten metal in their cores, but Mercury's field is too active for a core that should have cooled long ago. Some researchers propose that the mantle itself might be part of the dynamo, its strange composition conducting electrical currents in ways that amplify the core's weak signals. Imagine a planetary-scale circuit where the mantle acts as a semiconductive layer, its minerals juicing up the magnetic field like a cosmic amplifier. This would require a mantle riddled with conductive materials, perhaps even metallic veins threading through the rock like wires in a circuit board. The implications stretch far beyond academia. If Mercury's mantle truly is a sulfur-rich, metal-laced anomaly, it could redefine how we search for habitable exoplanets. Worlds orbiting close to their stars might harbor similarly exotic interiors, their mantles behaving in ways our current models don't account for. Until future missions like BP Colombo deploy ground-penetrating radar or seismometers, Mercury's mantle remains one of the solar system's great unsolved riddles, a hidden layer whispering tantalizing clues but refusing to reveal its true nature. Mercury's gravity field tells a story that doesn't always match the surface. We see regions where the planet's pull strengthens or weakens unexpectedly, as if hidden forces are tugging at the rules of physics itself. These gravitational anomalies, mapped in exquisite detail by NASA, a messenger spacecraft, reveal a world of contradictions. Vast impact basins that should weigh less actually exert stronger pulls, while towering volcanic plateaus sometimes register as gravitational ghosts. It's as if Mercury's crust is a mask concealing subterranean secrets that rewrite the textbook on planetary structure. The most glaring example lies in the planet's northern volcanic plains, a smooth, seemingly lightweight region that somehow boasts gravity measurements 20% stronger than models predict. The leading explanation points to mass concentrations, or mascons, buried deep beneath Mercury's skin. These dense pockets of material, often lurking under impact basins, were first discovered on the Moon, lunar regions where ancient asteroid strikes excavated crust so violently that denser mantle material surged upward, creating permanent gravitational bullseyes. But Mercury's mascons defy that template. Some correspond to visible craters, but others appear where the surface shows no signs of trauma, suggesting hidden asteroid impacts erased by lava flows or weirder processes. The Caloris Basin, Mercury's grandest impact scar, hosts a mascon so massive it skews the planet's gravitational field like a hidden lead weight sewn into a pillow. Yet MESSENGER's data revealed an oddity. The mascon's center doesn't align perfectly with the basin's midpoint, as if whatever lurks below slid sideways after the impact like syrup on a tilted plate. Density variations in Mercury's crust add another layer to the puzzle. Unlike Earth's relatively uniform outer shell, Mercury's crust appears patchworked with zones of radically different composition, some rich in iron sulfides, others laced with lightweight silicates. These disparities create gravitational ripples detectable from orbit. The planet's sprawling smooth plains, for instance, register as gravitational lows despite their youthful surfaces, hinting at porous, foam-like layers beneath. Meanwhile, the enigmatic, high-reflectance red spots, mysterious bright regions tied to possible volcanic vents, coincide with localized gravity spikes, as if ancient magma plumes left behind dense mineral roots. The wild card in this gravitational tug-of-war is Mercury's core. Its oversized iron heart isn't just a static lump. It's dynamic enough to generate a magnetic field, suggesting at least part of it remains molten. Some researchers propose that the core's sloshing motions, driven by tidal forces from the Sun, might subtly deform the crust above, creating gravity fluctuations that migrate over centuries. Imagine a waterbed where shifting weights beneath the surface make waves ripple unpredictably across the mattress. This could explain why certain anomalies don't correlate with any surface feature. They might be fingerprints of deep, slow-motion convulsions we've yet to fully model. What makes these anomalies more than academic curiosities is their window into Mercury's violent evolution. Mascons record ancient cataclysms frozen in gravitational amber. Density variations trace the planet's volcanic pulse, from fiery outpourings to final gasps, and those uncorrelated spikes, they might be clues to processes we've never seen elsewhere, a reminder that even in gravity's rigid laws, Mercury finds ways to surprise. Until future missions like BP Colombo map these quirks in higher resolution, they'll remain tantalizing breadcrumbs leading to a truth just beyond our grasp. Of all the cosmic debris raining down on Earth, chunks of Mars, samples of the Moon, even rare fragments of Vesta, none bear Mercury's signature. This absence is more than curious, it's statistically bizarre. Given Mercury's battered surface and proximity to Earth, we should have found at least a handful of its meteorites by now. Yet every candidate tested turns out to be from elsewhere, leaving planetary scientists grappling with a cosmic whodunit. Where are Mercury's missing pieces? One theory points to the Sun's ruthless gravitational grip. When impacts blast material off Mercury, the fragments don't just drift, they are flung into chaotic orbits where the Sun's influence dominates. Unlike Mars or the Moon, whose ejected rocks can coast toward Earth on relatively stable trajectories, Mercury's debris faces a gauntlet of orbital hazards. The planet's velocity, an average 30 miles per second, means any ejected material inherits that blistering speed. Combine this with the Sun's overwhelming pull, and most fragments either spiral inward to vaporize in solar fire or get slingshot out of the inner solar system entirely. Picture a child trying to toss a ball from a speeding train. Unless thrown at just the right angle, it'll veer wildly off course. Atmospheric obliteration offers another grim fate. Mercury's surface rocks, forged in the solar system's furnace, are likely packed with volatile minerals like sulfides that crumble under Earth's atmospheric entry. Unlike hardy Martian basalt or lunar anorthosite, which can survive the fiery plunge, Mercury's debris might shatter or vaporize during descent, leaving no recognizable remnants. Some researchers suggest we might have already collected Mercury meteorites without realizing it, their unusual composition misclassified as oddball asteroids or terrestrial contaminants. But the most tantalizing possibility involves a celestial game of pool. Simulations show that Mercury fragments ejected at specific angles could get trapped in orbital resonances, bouncing between Venus and Mercury for millennia before finally escaping. A few might even reach Earth, but so sparsely that finding one becomes a needle in a haystack scenario. Others could be hiding in plain sight, lurking in museum collections or embedded in ancient sediments, awaiting advanced isotopic analysis to reveal their true origin. The stakes go beyond academic curiosity. Mercury meteorites could unlock secrets about the solar system's violent youth, from the composition of its primordial crust to the timing of the late heavy bombardment. Future missions might finally settle the debate by identifying unique isotopic markers, perhaps a telltale ratio of lead isotopes or solar wind-implanted gases, that distinguish Mercury's material from everything else. Until then, this absence remains a silent challenge, reminding us that even in a universe littered with debris, the rarest fragments often hold the most precious stories. Mercury has proven itself the solar system's ultimate trickster, a world that looks simple at first glance but hides layer upon layer of cosmic riddles. As we wrap up this journey, let's revisit the 5 most baffling mysteries that make this tiny planet an oversized enigma. First, the hollows, those glowing pits that pepper Mercury's surface like celestial bullet holes, defying erosion and replenishing their volatile contents against all odds. Then there's the planet's absurdly massive core, a molten metal monstrosity that shouldn't exist in a body this small, yet somehow powers an active magnetic field against relentless solar fury. Don't forget the chaotic terrain, a nightmare landscape on the exact opposite side of the planet from the Caloris Basin, as if Mercury itself cracked under the stress of an ancient cosmic punch. And who could overlook the polar ice gleaming reservoirs of water hiding in permanent shadows just a stone's throw from the sun's blistering flames? Finally, Mercury's gravitational gremlins, those unexplained mascons and density variations that warp its pull like hidden lead weights sewn into its crust. What ties these mysteries together isn't just their strangeness, it's how they force us to rethink planetary science. Mercury laughs in the face of expectations, proving that even the smallest worlds can harbor the grandest surprises. Its contradictions, scorching yet icy, geologically dead yet dynamically alive, stripped bare yet chemically rich, make it a masterclass in cosmic paradoxes. Every mission we send there peels back another layer, only to reveal fresh questions scribbled beneath. Now it's your turn. Which of Mercury's enigmas fascinates you most? The ghost volcanoes, the sodium tail, or something we didn't even have time to cover today? Drop your thoughts in the comments below. I'd love to hear which mysteries keep you up staring at star maps. And if you're hungry for more cosmic conundrums, hit that subscribe button because the universe is overflowing with stories stranger than fiction. From diamond rain on Neptune to the hexagonal storm on Saturn, we're just getting started. Until next time, keep looking up and remember, sometimes the biggest secrets come in the smallest packages.